Hello, I'm Seok-Ki Jung from the Department of Orthodontics at Korea University. Thank you very much for coming to the webinar. Uh, this presentation is collaborated with WebCeph. Let me introduce to you WebCeph quickly. This is the WebCeph URL. It is a web-based orthodontic and orthodontic platform. The service is free for now. If you use the invitation link at the right bottom corner in WebCeph, you will automatically be WebCeph friend with your friend by clicking the link. Please use WebCeph a lot and introduce it to others around you. Thank you. Once again, I'm Seok-Ki Jung from the Department of Orthodontics at Korea University. Today's topic is artificial intelligence in orthodontic diagnosis. And this presentation is with WebCeph. The information above was published in the American Journal of Orthodontics and Dentofacial Orthopedics in January 2016 under the heading of New Approach for the Diagnosis of Extractions with Neural Network Machine Learning. Do you like Go? In March 2016, there was a Go game between Isedo and Google's AI AlphaGo. It was called the Confrontation of the Century. Did you see it? Until that time, Go was considered to be a field that AI is hard to surpass. Therefore, it was expected that Isidore would win. However, AlphaGo surpassed Isidore with his perfection. It was rather surprising that Isidore won one game in this game. Since then, artificial intelligence has evolved to the point where it is difficult for a person to win, even with a two-point game. A detailed algorithm for AlphaGo is presented in this paper. To briefly explain the algorithm, it is based on a policy network and a value network based on artificial neural networks. The policy network selects the next best position among the number of cases, and the value network is an algorithm that calculates the probability of victory based on the current pattern of stones on the board. By these two, it is continually determining the next position and calculating the current victory probability to determine the next position in the direction of continuously increasing the probability. Have you seen this movie? The movie AI, which is one of my favorite movies. This is the story of David, an artificial intelligence robot that has no difference from a person in the far future. The poster phrase, his love is real, but he's not, caught me sight. So, artificial intelligence, machine learning, deep learning, these are very hot keywords these days. The world's leading companies, including Google, are doing their best to develop artificial intelligence. What exactly is artificial intelligence, and how much do you know about artificial intelligence? And how is artificial intelligence implemented, and how is it applied to the real world? I hope it's an opportunity to think about those things for a moment. This is introduction. The most important part of orthodontic treatment is to determine the treatment plan. Since extractions are irreversible, a prudent decision is required. Generally, most orthodontists make a decision with data from the clinical evaluations, photographs, dental models, and radiographs based on their experience and knowledge. Thus, the decision depends on the practitioner's experiences in many cases. If it is possible to share decisions of the experienced practitioners, that would be helpful. However, decisions cannot be standardized with some combination of measurements. Thus, another approach is needed. Many types of expert systems have been developed for decisions. Among them, machine learning based on artificial intelligence techniques is the most widely used form. There are a lot of different methods in this type of machine learning. I tried to perform extraction diagnosis with a machine learning method using a neural network. The human nervous system consists of neurons. Each neuron meets and receives information from synapse. This information is integrated within the complex neural networks that make up the network, and sometimes it is reduced and sometimes reinforced to create information. Artificial neural networks are created by mimicking these human neural network systems similarly. The artificial neural network consists of several nodes and their connections. It would be easy to understand if you think that nodes mean each neuron and connection means synapse. The artificial neural network consists of three layers. The first is the input layer, which is the layer that receives the input signal. The second is the output layer, which is the layer that produces the output. And lastly, there is a hidden layer that exists between input and output and acts as an intermediary for information. You can think of it as a kind of interneuron. Based on these artificial neural networks, let's look at how machine learning is done. When information is transferred from each node to the next node, the input value is multiplied by the weight. Multiple information delivered to one node are integrated. The output obtained in this way is compared with the true value, and the weight is adjusted based on this result. The set that trains the system is called the training set, and by repeating learning with the training set, the artificial neural network is built. With this system, the neural network will be able to provide an appropriate answer to the question that comes in later. In more detail, the input vector is multiplied by the weight vector. The sum of the weights is obtained, and then the bias vector is added to obtain the final value. These values are passed through the activation function to create an output. You can think of passing an activation function as a kind of action potential. Since it is meaningless that the value of each node falls outside a certain range, you can understand this of standardizing the value of each node to a numerical range between 0 and 1. The purpose of this study was to create an artificial intelligence decision model for extraction diagnosis using neural network machine learning and evaluate its validity and accuracy. Material and methods. A total of 156 patients were sampled. Exclusion criteria excluded cases with unerupted permanent teeth, missing teeth, and malformed teeth, previous orthodontic treatment history, and maxillofacial deformity, and orthodontic surgery case. The inclusion criteria were for people with the following 5 treatment plans: non-extraction, maxillary and mandibular first premolar extractions, maxillary and mandibular second premolar extractions, maxillary first premolar and mandibular second premolar extractions, and lastly, maxillary first premolar extractions only. Okay. Of the total 156 samples, 96 samples were for learning, and the test set for evaluation were 60. Learning set was divided into training set and validation set. Reasons to divide the validation set are as follows. If you repeatedly learn through a specific training set, the correct answer rate for that training set increases. In the graph, the error only goes lower. At the same time, however, as a model specialized only for the corresponding training set is created, the rate of correct answer for other sets will drop. This phenomenon is called overfitting. To prevent overfitting, a validation set to validate the model is placed and the correct answer rate for the validation set is checked. When the error for the validation set is the lowest, the training is stopped and a generalized model can be obtained. In the validation process, the validation set is changed from the learning set, and the rest are set as the training set for training. By creating multiple models like this, the best performing model is adopted. In this study, an artificial neural network with 18 input nodes, 4 hidden nodes, and 1 output node was used. I performed the process of adjusting the weight by comparing the error with the true value using the backpropagation algorithm. Also, the sigmoid function, as shown in the figure below, was used to activate function. These are the measured values used as input nodes. A total of 12 separametric variables and 6 additional indexes were used. Of the SEP measurements, 12 measurements were used, including skeletal measurements, dental measurements, and soft tissue measurements. 6 additional indexes were used. The first and second are the arch length discrepancy index of the maxilla and the mandible. As explained in the activation function, each node should be standardized with a value between 0 and 1. So it is grouped according to the ALD value and assigned a number. The more severe crowding is assigned to the value closer to 1. The third is the molar key index. The numerical value was assigned according to the molar key. And the closer to the class 2 key, the closer the value was assigned to 1. The first is a large overjet index. If it is over 5 millimeter, it is classified as severe, and a value of 1 is assigned. The fifth is protrusion index. The more severe the protrusion, it is assigned to the value of 1. Lastly, it is about whether there is a protrusion in the patient's chip complaint, and if there is a protrusion in the chip complaint, 1 is given, otherwise 0 is given. Okay. Next is the output node. The output node consists of 3 bits in total. The first is DX extraction, which is a bit that divides extraction and non-extraction. If it is 0, it means non-extraction, and if 1, it means extraction. The second is DX difference, which is a bit that distinguishes the case where the upper and lower teeth are extracted equally and the case where the teeth are extracted differentially. If it is 0, it means the extraction like 5-5 or 4-4, and if it is 1, it means the extraction like 4-5 or only maxillary extraction. Finally, DX more is a bit about whether more retraction is needed. If 0, a smaller amount of retraction is needed, such as 5-5 or 4-5 extractions. If 1, a larger amount of retraction is required, such as 4-4 or only maxillary extractions. Based on this, a stepwise system was constructed with a total of 4 machine learning models. When data comes in, the first bit of the output is determined through the first classifier. Through this, non-extraction and extraction are divided. If you pass the second classifier with extraction data, the second bit of the output is determined. Through this, the differential extraction between the upper and lower teeth are determined. Finally, when the classifier is applied to the same extraction and differential extraction respectively, the final bit of the output, DX more, is determined. Through this, it is divided into 5-5 and 4-4 extractions in the same extraction. and 4-5 extractions and maxillary-only extraction in the differential extraction. When data is classified as above, the success rate of extraction diagnosis is calculated by comparing with the actual diagnosis. Okay, it is results. The learning curve of each classifier is shown. As predicted, errors in the training set indicated in black decrease as the training progresses, and errors in the validation set indicated in blue decrease and increase again as the training progresses. When the error of the validation set was the smallest, the learning was stopped and the model was selected. Through the cross-validation process, 4 classifiers with the highest performance among the selected models were selected as the final model. This shows the success rate of extraction diagnosis of the final model. In the case of classifier 1, which divides extraction from non-extraction, the success rate was 92% in the training set, 94% in the validation set, and 93% in the test set. In the case of classifier 2, which divides the same and differential extractions, it has a success rate of 89%. For classifier 3, which determines the severity at the same extraction, the success rate is 84% in total. And for classifier 4, which determines the severity of the retraction, it has a total success rate of 96%. After all 4 models were successfully diagnosed, the success rate was 85% in the learning set, and 82% in the test set, and 84% in total. Among 156 patients, 25 failed the diagnosis. As a result of analyzing the failed diagnosis, extraction of 4-4 and 4-5 confusion were the most common cases, followed by non-extraction and 5-5 confusion, followed by 6 cases. And analyzing the results of the failed extraction diagnosis, most of the failures occurred in the borderline case. In 21 of the 25 cases, even though the results through machine learning were diagnosed, there seemed to be no problem. Given this, the clinical success rate has increased significantly. Okay, discussion. Jae had used artificial neural network modeling for determining extraction or non-extraction. However, in this study, we also determined extraction positions. Furthermore, the decision-making success rates were improved. In the previous study, the success rates were 100% in the training set and 80% in the test set. The difference of these success rates could mean overfitting. To minimize overfitting and to verify the fitness of the model, the samples were divided into the learning set and the test set from the beginning in this study. In addition, the learning set was divided into the training set and the validation set to make a generalized model. As a result of this, the success rates of the training set, the validation set, and the test set were similar in this study. It implies that the model was generalized better. Although step-by-step learning had the shortcoming of accumulating the errors, the goodness of it was better than one-step learning. It was because the simpler system might have a higher success rate. In addition, a case that failed previous step tended to fail also with next step. Thus, accumulation of errors could be minimized. Okay, the success rates of the classifiers were 93% for the diagnosis of extraction versus non-extraction, and 84% for the detailed diagnosis of extraction patterns in total. Artificial intelligent expert systems with neural network machine learning could be a new approach in orthodontics. Using this approach, I also wrote a paper related to surgery versus non-surgical diagnosis and was published in the Journal of Craniofacial Surgery in 2019. Similar to the diagnosis of extraction, it is initially divided into surgery and non-surgery. Then, in the second classifier, Class 2 and Class 3 are classified. The third classifier was divided whether or not extraction was necessary for the surgery. As a result, there was a high success rate of 95.8% in the classification of surgery and non-surgery, and a 91% success rate in detailed surgical diagnosis, including extraction. It does not end here. Recently, I published the article in Applied Science by writing a paper for surgery indications using deep learning. The biggest difference between the deep learning algorithm and the artificial neural network model shown earlier is the depth of the layer. As you can see in the schematic diagram here, a lot more layers are used. Also, the biggest difference from the existing research is that in the previous research, the diagnosis was based on the measured value, but in this research, the diagnosis was based on the cephalometric image itself. In other words, there is no need for a measurement process. AI detects the landmark on its own, selects the area deemed valid through the detected landmarks, cuts it, and uses it as an input. If you put the image itself in the deep learning model, the result of the diagnosis is displayed. In deep learning, a convolutional neural network is used, which extracts the characteristics of an image by passing a specific filter to the input image. It shows that extracted features after the original images in the top row pass the convolutional filters in the left column. The result of this feature extraction is learned through the artificial neural network shown earlier and diagnosed. In this paper, 3 different types of deep learning models were compared and analyzed. A model called Modified AlexNet showed the best results with 96.4% of surgery versus non-surgery diagnosis. This is slightly higher than 95.8% of the previous ANN model. In the past, AI models are like black boxes, so you can only see the inputs and outputs, and you couldn't look into them. But recently, there is a lot of research to develop explainable AI models. One of them was the technology that showed the most contributing part to the AI decision through the technology called CAM. If the diagnosis is successful, a specific area is activated as shown in the figure. If the diagnosis was unsuccessful, the activated area could be scattered. Okay, conclusions. Sorry. There is no correct answer for the diagnosis. The aim of this study was not to find the right answer. By mimicking the decision-making of experienced experts, the artificial intelligence expert system could be a reference for less experienced practitioners. Clinicians can choose whether to follow that decision. Moreover, it is also possible that expert systems can be made using various philosophies of diagnosis. That is another merit of artificial intelligence system. Thanks for listening. That's all I prepared. Do you have any questions? If you leave a question in the WebCeph forum or Facebook group WebCeph X with the comments, I will gladly respond it. Thank you very much for participating despite your busy time. This is the end of the webinar. One more thing. If you use the invitation link at the right bottom corner in WebCeph, you will automatically become friends with the person who pressed the link in WebCeph. Please use WebCeph a lot and introduce it to others around you. Thank you again.